So for today's class, we are going to be looking a little bit on a circle theorem. Usually there is one or so question on the paper about the circle theorem, but it's really a lot to digest. So we're going to start today with circle theorem and just see how far we can get. There's no rush to finish. We can finish on Monday or on Saturday, depending on, how we get through. So there is no rush to finish. It's going to be a lot to digest. So I just want to prepare you mentally for that. So I have drawn a circle. It's not a perfect circle, but you know what a circle ought to look like. And that boundary of the circle that we draw, what is it called? I'm assuming we all know what it's called. So this boundary of the circle, what's that called? That line that goes all the way around the circle, what's it called?
The circumference.
It's called the circumference. So this is called the circumference. So what I'm going to be doing is I'm just going to be going over just the parts of the circle, just very briefly, just so that because when we're doing circle theorem, there's going to be a lot of assumption that you know the different parts of the circle. So we're going to go through them so that you're more comfortable. So a circle is really a closed curve, right? And all of the points on a circle, in a perfect circle, this is not a perfectly shaped one, but in a perfect circle, all the points are equal distance from a center point, right? So all the points are equal distance from a center point. Now in a circle, if you should draw a line from the center to any point on the circumference. So for example, draw a line from the center to a point on the circumference. Sorry, that line was a little crooked, right? If you should draw a line from the center to any point on the circumference, the distance would be the same, all right? Doesn't matter where. I've drawn 4, it could have been 10 or 15. The distance would have been same. Any line from the center of the circle to the circumference measures the same distance, right? Now we call this radius. Everybody familiar with what a radius is? Come on, you're going to have to answer me,
Yes, miss.
Everybody familiar with what a radius is?
Yes, miss.
Great, thank you, Amoy. So the circumference, the radius is just a straight line from the center to any point on the circumference. So it's a straight line from the center to any point on the circumference. And it doesn't matter where this line comes from or where it ends up. As I've shown you 6 here, they're all the same distance, right? Equal distance. So circumference and radius, that's what we've done with that circle. Now we still have our center here and we have our circumference at the edge, right? Now for radius, we were drawing a line from the center to an edge of the circumference. Now we're going to be looking at a diameter. Well, we're going to be looking at the diameter, which is a line that passes through the center and touches 2 points on the circumference. So it's a line, you can call it a chord. I'll tell you what a chord is. Let me just draw this first. All right, so I'm trying to draw a couple just to give you some perspective. No, choose yellow. right? So I've drawn 3 diameters on this circle, right? One in yellow, one in pink, and one in multicolored. And for all of them, 3 things are true for the diameter, right? For all of them. For each of them, the diameter would cut the circle in half. Right? It cuts the circle in half. So if you focus on one of the lines, you realize that each of them cuts the circle in half. And that's because it passes through the center point of the circle. So that's the next point. It passes through the center point. For it to be a diameter, it has to pass through the center point of the circle, right? And the third thing is that it touches 2 points on the circumference. And I know these are stuff that you may know already, but I implore you to pay attention because when we start with the circle theorem, these things become important. So these are the features of a diameter. A diameter will cut a circle in half, and you don't have to try to make it cut in half. As long as you find the center of the circle and you draw a line that passes through the center and touches 2 edges of the circumference, you draw a straight line that does that, then it will automatically be a diameter. It's a diameter, and it will cut the circle in 2 equal halves. All right, any questions so far? All right, next thing. So I'm just going to draw back a center here. The next thing we want to look at is a line that it touches 2 parts of the circumference, but does not passes through the center. What do we call that line? Anybody have any idea?
R.
No, not an R. With the line we're talking, not the curved portion, the line.
Chord.
Chord. Right. So this is the chord. The chord is a line that it touches 2 parts of the diameter of the circumference. Sorry. So see, I put in that's 1 point, and that's 1 point there. It touches 2 parts of the circumference, but it doesn't pass through the center. It's called a chord. People mix up chord with diameter all the time. The difference with a chord and a diameter is that the chord does not pass through the center of the circle. And because it doesn't pass through the center of the circle, it doesn't cut the circle in half. Everybody follow? Yes, no, maybe. All right, let's look at this situation over here. I'm going to be having 2 chords, no, not 2 chords, 2 radii, right? So remember we said a radii moves from the center to one edge. So this is one radius. This is another radius here, all right? Everybody agree with me? Yes, no?
Yes, miss.
Great. So if a section, well, a section of the circle that is bound by 2 radius, what you call it? So let me just shade it. The inside portion of the circle that is bound by 2 radii, what you call it? This portion that I'm shading here. It's bound by 2 radii, what you call it? Hmm? No takers. All right, so the portion that is bound by 2 radii, that you see there, kind of like a pie shape, it could be any size, but if it's bound by 2 radii, it's called a sector. Easy to remember. Think about it like a section of your circle. It's a sector, all right? Now the sector is bound by two things. It's bound by the radii, which we saw the radii here. I had that in multicolored. And it's also bound by a piece of the circumference. What is this piece of the circumference called? Giovanni, you had said it earlier. What's this piece of the circumference called? Giovanni, you fall asleep?
An arc.
The arc, right? So this is an arc. An arc is a portion, a piece of your circumference, right? And we say for a sector is bound by two radii and an arc, right? And when we do measurement, we will go ahead and calculate it. Usually you calculate circumference, which is the distance of the entire circle, but you can also calculate an arc, which is just a piece of the circumference, all right? So we have gone through that. We know what a radius is. We know what a circumference is. We also know what a diameter is. We know what a sector is, a chord, and an arc. All right. So any questions before we move on? All right. So let's go. Let's get into our circle theorems now. Now, when we say circle theorems, we are literally talking about some rules that governs angles and measurements in a circle. Now, I definitely will caution you that initially circle theorem will feel overwhelming. It's not something that you will get into your bones, definitely not without practice, all right? Because there's so many of these theorems, there's so many of the rules. There are about, I would say about 9 of them. There's so many of them that, and when you get a question, you have to sort of flip through the different types of theorems in your mind and see which applies to each question that you can use. So what we're going to do, we're going to go through all the theorems. We're going to go through all these theorems today, and we're going to start the process of working some questions, because guess what? This is one of those topics where working question is your only way out. So let us start with our first theorem. So I'm going to start and number them to keep track. So and my stuff not drawn to scale. You hear? Absolutely not drawn to scale. All right, so starting with some easy theorems here. So this here is the center of our circle. You can call this B, C. You can call this D. You can call the center A. So the first theorem says that if we have an angle that is subtended by a center arc, let me write that word up here because you're going to be hearing it a lot. An angle that is subtended. And all that means is that an angle is formed from the extremities of a certain point, right? That's all it means, right? The line, it's like the line segment or any other section of the curve where the line will pass and make an angle, right? So it's basically saying the angle is made around this area here. So here we have 2 angles. So if we can just, I'm going to use the highlighter to sort of track it. So we have one angle here, angle B, right? A and C. What is seeing that? So this is one angle right here. And then we have another angle, which is angle B, which is angle B, D, and C. So that's another angle right there. Now, this theorem or rule, it states that, well, if we look at these two angles, we can see that both angle is subtended by the same arc. So what that means is that both angles are formed around the same arc. So let me just highlight that. This is the arc, right? We had said this is the arc. So both angles are subtended by the same arc. They are formed around the same arc. We have BDC formed by the same arc, BAC formed by another arc. Now, in a case where you have two angles subtended by the same arc, meaning that they form around the same arc, and one of those angles pass through the center. In our case, it would be this angle here that's passing through the center. Everybody following so far? You need to open your mics and answer. You know, this is something that I don't want you to keep silent. Answer. Please respond. Are you following so far?
Yes, miss, so far.
Am I, Giovanni? All right. So the angle is subtended by the same arc. Now, what the rule says is if one of them passes through the center and another doesn't pass through the center, the one that passes through the center, the angle of the one that passes through the center is twice as big by the one than the one that doesn't pass through the center, all right? So let's get that. The prerequisite for this to apply is that they must be subtended by the same arc. They must be formed around the same arc, all right? And these two qualify. So they must be formed around the same arc, and one of the angles must pass through the center of the circle. Now, in this case, both of those requirements are met. So what it is saying is that this angle here, which is BAC, the one that passes through the center, is 2 times as big as the one that doesn't pass through the center, all right? So effectively, these theorems are telling you some relationships that exist between angles in a circle, providing that certain prerequisites are met. So let me say it again. In this case, 2 prerequisites. 1, both angles must be formed around the same arc. That's the case here. I've colored that in yellow. One of them must pass through the center. That's the case for the angle in blue. If that is true, then there's a certain pattern that holds, and that pattern is that the angle that passes through the center is 2 times as big as the one that doesn't pass through the center. So if the angle that passes through the center, in our case, the angle that passes through the center is angle BAC. Everybody recognize that? Angle that passes through the center here is angle BAC. So if angle BAC is 100 degrees, based on this rule, what is the size of angle BDC?
50?
It would be 50 because angle BAC would be twice the size of angle BDC because they meet the criteria. Everybody understand that? Giovanni, Amoy, please start back to me. None of them not talk back to me. In a similar way, let us say you get the angle BDC. You got that BDC was equals to 75 degrees. What would be the size of angle BAC? Your question gives you that BDC is equal to 75, and it asks you to find what is BAC.
Would be 150?
It will be 150. You'd multiply that by 2, right? And you'll get 150. Because the angle that passes through the center of the circle is 2 times as big as the one that doesn't, as long as they're bound by the same chord, the same arc. Any questions on this rule theorem? All right, let's go to our next one. I want you to understand them individually, because when you get the questions, it's gonna look not so hot. Foolishness. All right, so that looks like it can work. All right, so in this case, we have a chord. I'm going to call the chord A and B, right? And we are seeing the chord. The chord is this here. It runs from one end of our circle to another end, but it's not passing through the center, so that's a chord, right? So we have a chord AB, and then we have two angles. So I'm going to call this one C and this one over here D. All right. Now this rule says that angles that are subtended at the circumference in the same segment by the same arc, they are equal.
If you're breaking up, I'm not hearing you.
Not sure why. All right. Hopefully you can hear me a little. Yeah, you hear me a little better now?
Yes, I'm hearing you better now.
All right, great. So this one says that angles that are subtended at the circumference in the same segment mean that they're in the same side, right, of the chord, in the same segment by the same arc are equal. So let's identify our arc. I'm just going to highlight our arc here in yellow. So this is the arc there, right? And it is subtended at the circumference, meaning that it is bound by a line of some sort. In this case, that's our chord AB. So that's that, right? So what the rule is that angles that are bound, if they're in the same segment, meaning that they're on the same side of this chord, right? Which both of these angles are, ACB and ADC are on the same side of this chord. As long as they're bound by the same chord and they're in the same segment, the size of the angle is going to be equal. So this angle and that angle would be equal angles, all right? So that's written properly would say that angles A, C, D is equal to angle A, D, B. Any questions? Now, I want you to also appreciate that when you are doing these questions on your exam paper, it will say not drawn to scale. And that's important for you to always realize, because you can't, a lot of times persons want to look at the circle and to try and infer from what the sizes are, etc., etc. Don't do that. Use the rules, apply the rules, the theorem, the circle theorems to give you your answer, because the circles are not drawn to scale. So whether or not these two angles look like they are the same size to you, based on the circle theorem, they are subtended by the same arc and they're in the same segment, so they are equal. So if one is 50, the other one is equal to 50 as well. If one is 80, then the other one is equal to 80. If one is 25, the other one is 25, and so on and so forth. Any questions? Any questions? Right. Let's go on to our third theorem. What? Right, no. So we're going to be doing our third theorem. Give me a minute, please. All right, let's go. So I'm going to be drawing my center here, right? Not drawn to scale. Don't hold me. Wait. All right, that's bad. All right, something that's a bit. All right, you know what I'm going to do? I'm just gonna draw a line. I don't know why I can't draw the line straight though. And then I will put that last. All right. So this is my center. This is my circle. This is my center. And I'm having a line. I'm going to call this line AB, right? It runs through the center of my circle and it touches two points on the circumference. Is this line a chord or a diameter? Chord or diameter? AB. Runs through the center and touches 2 points on the circumference. It's a diameter, right? Runs through the center, it's a diameter. So I have my diameter. This line is a bit squiggly. It's not meant to be, all right? And I'm gonna call this one up here, I'm gonna call it J. All right, so let's go now. So this rule applies, or this theorem applies when you have an angle that is subtended at the circumference by the diameter. All that means is we have an angle that is formed around a diameter. So in this case, our angle is AJB, right? So that is AJB. So our angle is somewhere, is right here, right? And it is formed around our diameter. That's what it means. It's subtended at the circumference. It touches the circumference. That's important. Subtended at the circumference by the diameter. So it touches the circumference and it is bound by the diameter. Now, the rule for this angle is that if this ever happens, the angle that is formed, irrespective of what it looks like to you, it is a right angle triangle. So it is going to be equal to 90 degrees, right? For this to be true, remember, it must meet two criteria. It must touch the circumference, and I'm putting it in a little layman's term for you. So it must touch the circumference, 1, and 2, it must be bound by the diameter. In this case, both are true. So we can see it touching the circumference up here, highlighted in blue, and we can see it bound by the diameter. I highlight that in pink, in yellow. Right here. Any angle that does that, it is the angle is 90 degrees, a right angle. And the point to be made about touching the circumference is very important because you can have an angle subtended by the circumference that does subtended by the diameter that doesn't touch the circumference. You can have something like that, right? In this case, this angle here would not be this angle, pink one, it wouldn't satisfy the requirements of this theorem, so it would not be equal to 90 degrees. You'd have to find a different way to find the size of this angle. Follow?
Yes, miss.
Amoy and Giovanni has gone quiet on me. Are you guys understanding?
Yes, miss.
All right, Giovanni? Understanding?
Yes, miss.
Not present. All right. So let's do our fourth theorem, right? All right, number 4. All right. So here we have a quadrilateral. Quadrilateral just means a 4-pointed polygon, a polygon, a polygon, sorry, that has 4 sides, right? Four points, 4 vertices. So we have a quadrilateral within a circle. Now, importantly for this theorem, the quadrilateral must have all 4 vertices on the circumference. So here, it must touch it. The vertex of the all 4 vertices of the quadrilateral, it must touch the circumference. So this rule doesn't apply. I'm just going to draw another one here. This rule doesn't apply if you have a quadrilateral that goes like this and that, right? In this case, you only have 3 vertices touching, right? You have this one, that one, and that one, but you don't have this one touching. And so this one, the theorem wouldn't apply to it, right? The theorem only applies to quadrilaterals within a circle where all the vertices are touching the circumference. And I have highlighted that in pink here, all right? So I'm going to label our quadrilateral E, F, G, H. So this is our quadrilateral. It's within the circle and it has all its vertices touching the circumference of the circle. Now, when this happens, I'm going to just jot that down over here because these are important prerequisites for the theorem to be applied. It can't be applied if these prerequisites are not met. So the quadrilateral, just going to put quad for now, should be inside the circle. Part of it can be outside or anything. And all 4 vertices must touch the circumference. Circumference. Right. So once that applies, once that holds, then certain other things we can deduce about the angles. We know that the opposite angles would be equal to 180 degrees. So those would be the opposite angles. So meaning I want to put them in colors together. This one and that one, which would be angle GHE. So this one here, I'm going to color it in pink. And this one, and EFG, they would sum to 180. If you add them together, they will be equal to 180, right? So let me just write that down. So angle GHE plus angle EFG will be equal to 180 degrees. Everybody following me? And then the same would be true. The same would be true for this angle here and its opposite angle, right? So for those, these two here, the ones in orange, they would sum to 180 as well. And they are, let me see, they are angle H, E, F plus F, G, H. They're equal to 180 degrees. Anybody have any questions so far? So if, let us say for argument's sake, that this angle here, EFG, was 70 degrees, what would be the size of angle H? Anybody? Simple maths. Opposite angles in a quadrilateral inside a circle where all vertices touch the circumference, they're equal to 180. So if EFG is equal to 70 degrees, what's the size of this angle over here? EHG.
70 degrees.
Huh?
Hold on. If the other angle would be 70 degrees, but the angle EFG is 70, then angle EHG is supposed to be 110.
110. They should sum to 180. They should add up to 180, right? So let us say angle HEF, which is this angle here, is equal to 93 degrees. What is the size of this angle here? It's opposite angle. Giovanni, this one is yours. Opposite angles in a quadrilateral that's inside of a circle where all the vertices touches the circumference is equal to 180 degrees. So if this angle in orange here is equal to 93 degrees, what is the opposite angle? The angle FGH, what's that measured? Giovanni, do I have an answer? Anybody else have an answer?
87 degrees.
Plug it in your calculator. So that again, Shana, you can low.
87 degrees.
87, I'm going to trust you. I didn't check it. So I'm
Can
going
you
to trust.
Yes, it's 87. It's 87 degrees.
Okay, excellent. So this will be 87 degrees here because the opposite angles, they should sum to 180 degrees. All right. Questions on this one? All right. Let's move on to our, what would that be? Number 5. I don't think I'm going to do all of the theorems. I think I'm going to break a bit and then work some questions and then come back and do some more theorems just so that it doesn't get too mundane for you. All right. So let's go through this one. All right. So this theorem has to do with, again, you have a quadrilateral that is inside of a circle, and all four vertices are touching the circumference of the quadrilateral. The difference with this one is we're looking at an exterior angle of a quadrilateral. So all that is, as you can see, I have extended one of the angles here, and we're measuring the exterior angle, which is an angle outside of the quadrilateral, right? So it's yeah, an angle outside of the one of the angles of the quadrilateral, right? So what happens in this case is when you have this situation where you have a what we call a cyclic quadrilateral, meaning that the quadrilateral is inside of the circle, and its vertices are all its vertices are touching the circumference. It's called a cyclic quadrilateral. If you have an exterior angle to the cyclic quadrilateral and you have a size for that exterior angle, then the opposite interior angle is going to be equal to the size of the opposite exterior angle. So let me give you an example. Now this here, this angle here, let me just see if I can highlight it. I have shaded it and all, but this angle here is our exterior angle, exterior to our quadrilateral, right? Because our quadrilateral, I'm gonna highlight it in pink. This is our quadrilateral here. Oops. Yeah. So this is our quadrilateral here in pink, right? And we have this yellow angle that is exterior to that quadrilateral, right? Now, its exterior, this would be its interior angle, right? So if this is its interior angle, the opposite interior angle would be right across from it. Everybody seen that? That's the opposite interior angle, right? The rule says that the size of the opposite interior angle is, the size of the exterior angle is equal to the opposite interior angle. All that means is that if this angle here is 55 degrees, the interior opposite angle, so this would be the interior opposite to the interior angle, would also be 55 degrees, right? You can have an exterior angle for any of your four interior angles, right? So what that means is I could have easily extended this one and I would have had an exterior angle, or I could have extended this one here to get an exterior angle, or this one, right? Any one of them I could have had an exterior angle for, but the rule would remain the same. Whatever the size of the exterior angle, the outside angle, I find the interior and then find the angle opposite to that interior. Both of the exterior angle and the opposite interior angle would be equal. Any questions on that one? All right, so that's the theorem for that one. The interior angle of a cyclical quadrilateral is equal to the interior opposite angle. All right, any questions before I move on? Questions?
Okay.
Any questions or anybody else? That's what, 5, this is 6. So we've gone through 5 theorems so far. We are going to be working some questions soon. Just want to give you just a few more theorems so we can have a good batch of questions to start to work through. So let's keep going. All right. So this line from the center to one point on the circumference that I'm highlighting pink, what is that line called? Amoy, Giovanni, what's that line called? From the center of the circle to one point on the circumference.
Yeah. Radius.
It's called a radius. Great. So here we have our radius. We didn't look at this line, but this line is a line that is exterior to the circle. It touches the circle, but it doesn't cut through the circle. So this line right here on the outside, anybody know what it's called? It touches the circle at a point, but it doesn't cut through the circle. What's this line called? This line here, so touches the circle on the outside, but it doesn't cut through the circle. Cut through the circle would mean like it cut through the circle like that. So it doesn't do that, but it touches the outside of the circumference at a point. Anybody know what it's called? Any guesses? Ideas? No? It's called a tangent, right? And the place where it touches the circumference, it's usually one place. It doesn't look like that right now based on how I've drawn it, but I'm just going to highlight it, that place where it touches the exterior. This is called the point of contact. Right, because remember contact. All right. Because remember we're saying that a radius, a tangent, it touches the circle, but it doesn't cut it. So wherever it touches it, that's called the point of contact. Now, the theorem that surrounds this sort of setup right here is that your tangent is always perpendicular to the radius at the point of contact. What that means is, remember, you can have a whole heap of radii, you know? You can have radii going all along the thing, right? Remember we had said that, right? So you can have radius anywhere. The rule doesn't apply unless the radius is at the point of contact. So where the radius is at the point of contact, the radius and the tangent is perpendicular, right? So where, let me just write that down so you can appreciate it. So where the radius is at the point of contact, the radius and the tangent are perpendicular, right? Now, this is important because what is the type of angle that is formed when you have perpendicular lines? What type of angles are formed when you have perpendicular lines? Come. What kind of angles are formed when you have perpendicular lines? You don't remember nothing we're teaching you? You're not studying? Right angles. We even put the little something right here, so right angles, right? So what it means then is that where this line, where they meet, these are right angles. At the point of contact, right angles. So is giving you information about the angles in the area. That's what all the theorems have been doing so far, right? Giving information. In this case, if your radius is at your point of contact for your tangent, then the radius and the tangent are perpendicular. And then of course, where perpendicular lines, where lines are perpendicular, the angle at the where they meet is 90 degrees. Any question? Everybody fall asleep?
No, it's not falling
Not falling asleep?
asleep.
No questions? Sure? All
No,
right. Let us see. I guess we'll see when they what do you call that now? I guess we'll see when the questions start work out. All right, we're going to go to a different one now. All right. Say that again?
Is theorem with the number 7 or we did 6 a while ago?
Oh, I did 6 a while ago. Okay, 7. So many of them. All right, so that's 7. Thank you. All right, so let's go. Circle going to give me a little bit of problem. Whoa. Supposed to be a tangent. Okay. All right, so let's see what we can do here. My circle is too squarey, too boxy, so you're not getting it so good. All right, so in this case, we're having an angle that's between a tangent and a chord. So going to highlight our tangent yellow, right? So it's between a tangent, the tangent here. Remember the tangent is that line on the outside of your circle that touches it at a point of contact, but it doesn't cut through your circle, right? So this is your tangent right here. And then you have your chord. Your chord, we know, runs from one point on the circumference to another point on your circumference without going through the center. So an angle can be formed between what's this? The chord and the tangent. Now that angle is equal to the angle that is subtended at the circumference by the
Mr. Audience is going in and out again.
Go in and out again. So the angle, this angle here, is going to be equal to the angle at the circumference in the alternate segment, in the opposite segment. So we're talking about an angle in the opposite segment. So this is it's in relation to the chord. So remember the same segment would be the same side as this angle would be on. So if it were the same segment, it would be an angle at the circumference in the same segment, right? Which would be this angle right here. You following me? Because in the same segment, meaning that on the same side of the chord as the angle that we're under consideration, which is the angle between the tangent and the chord. However, the rule is not about the angle in the same segment. It is about the angle in the alternate segment or the opposite segment. So it's about the angle in the opposite segment that's made at the circumference. So it would be this angle here, made at the alternate segment in the at the circumference. So it touches the circumference and it's at the alternate segment. Follow me? I want you to get the location of the angle, right? So
can you repeat? Just repeat all of what you just
all right. So we're starting off looking at which angle we're considering. We're considering here an angle that is made between a tangent, and I have highlighted the tangent yellow, and a chord. So this is our chord here. That's so messy. So we have an angle that's formed between the tangent and the chord. I'm going to color it red. See it right here, so, right? Now this angle that's made between the chord and your tangent, it is equal to an angle in the opposite segment. Now, opposite segment, so let me just give you an idea of what we mean by opposite segment. We're considering this. So I'm drawing another circle, right? This is my chord. The angle I'm considering is this angle right here, which is this angle, the angle between my chord and my tangent, right? Now this angle is in this segment down here. Following me? So the segment is in relation to which side of the chord, right? So it is in this segment here, right? The rule says that the angle that is formed between the chord and the tangent is equal to the angle at the circumference. That means the angle has to be made on the circumference. And we're seeing the angle being made at this circumference here, but it has to be in the opposite segment. So it can be in this segment down here because this is the same segment like the this is the same segment as the angle. It has to be in the opposite segment, which is this segment here, opposites to where the angle under consideration, the angle that the rule is about, has to be in the opposite segment to that angle, which is not in this segment here, but in this segment here up here, right? Remember, the chord is what determines the segment. So this is a line. This is one segment, one portion of your circle. The top part is another portion of your circle. The angle, the red angle here, that is made between the tangent and the chord is in the bottom segment. The rule says that the angle that is in the opposite segment at the circumference is equal to this angle here. So what that means is that this angle here, which satisfies those criteria, is the same as the red angle. Any questions?
No, miss, understand.
Oops. So I'm going to write down the rule just so you can see it. So you have, so let me just give it some names. So this is this, we can have this chord be A, B, right? So this chord is AB, and this vertex of the triangle here, that's C. So what we're saying is the angle that is at B, angle that is at B, between B and this tangent here, is the same as the angle that is at ACB here. The one in red is the same as the one in blue. The theorem that governs that says the angle between a tangent, so a chord can hold, and a tangent is equal to the angle Angle. The angle subtended at the circumference. So the angle made at the circumference, which is C, we're seeing up there, it is at the circumference, right? By the same chord, because it's made by this chord, chord AB, and it is in the opposite segment. All right. So that is the theorem there. Now, you're learning all of these in isolation now. However, when you start working them, you don't be worried if when you look at a question, you can't place what theorem to use. It is literally going to take you going back, flipping back through to the theorems and seeing which one will match a question until you've done enough questions now where the theorems become sort of second nature. All right. So don't worry if you don't get them right off the bat. So we have 2 more to do, and then we're going to start working some questions. So this would be 8 then. All right. All right. So let's go through this one a little bit. Now, this rule is concerning the line that is joining the center of a circle to the midpoint of a chord. So I am going to just highlight the center of the circle here in blue. Our chord, remember we say a chord touches 2 ends of the circumference without passing through the center of the circle. So here our chord is AB. I'm going to highlight our chord red. Red is a little bold, but we'll work with it. So AB is our chord. It's there in red. And this rule says the line, any line that joins the center of a chord to the, well, that joins the center of a circle, which in our case is blue, to the midpoint of a chord, which is here that I have placed in black. Let me just put it, see if I can put that different color. Midpoint of a chord, it's in yellow. That means, remember, a chord is a line, so it's literally the middle of the chord. So if you have a line that joins the middle of the chord to the center of your circle, the resulting angle between that line is going to be 90 degrees. What that means is that the lines are going to be perpendicular, literally. You're joining the center of a chord. That's too messy. You're joining the center of a chord. So you have a chord, you're joining the center of it, and you have the circle in the center here. You're joining it together. The lines that join the center of a chord to the center of your circle is going to be perpendicular lines. So the angle is going to be 90 degrees. And I have, as I've drawn it here, it is in an orientation that you can appreciate that it can be, it actually is 90 degrees. But you may get questions where it's not that straightforward, yeah? Where it looks more like that, or it looks a little slant. So I'm saying that to make the point that, remember, it's not about what it looks like. These things are never drawn to scale. It's about what theorem you can apply. Read the question, pull the information. If they tell you that this is the center, which is O, this is the midpoint, then you know that any line that joins the midpoint to the center, the resulting angle is going to be a 90-degree angle because the lines will be perpendicular. Any questions? All right, no questions. So this now is going to be number 9, which is our last one. All right, it's not going to work. Yeah, all righty. So when we looked at, I think it was rule number 6, this one, we learned that wherever the radius touches a point of contact for a tangent, the angle that is formed is 90 degrees. So because this is our center, I'm going to call our center O, then this from O to this end here, that would be a radius, and we see that this is a tangent with a point of contact. So this angle here, we know is 90 degrees, just based on, not this rule, but just based on the rule, the previous rule that we had gone through, right? So we know, again, this is a radius here, and this is a tangent. So this is going to be a 90-degree angle. So the rule says that the lengths of two tangents to a circle from an external point on the circle are equal. So let's look at what that says. The lengths of two tangents to a circle from an external point to the point of contact is equal. So let us say, so first of all, let's call this external, this is P. Let's say this is P. This is Q here. This point of contact here, that is Q, and this point of contact here is R. So the rule is saying that the length of two tangents to a circle, so the tangent to the circle, two tangents you have here, QP and PR. So the length of both of them from an external point to the point of contact. So here our external point, external to the circle. The external point is P to the point of contact, which is R. They are equal. So what we can say here is that QP is equal to PR. Everybody is comfortable with that? All right, because the rule just says that they're equal. Now, the other thing to consider is if we have a bisector, so if we have a line that bisects from, that runs through the middle, so this line would be OP, that OP, that, well, OP, the line OP that I have it in, what's that, broken line right there, it bisects angle QPR, which is QPR, it cuts QPR, and it cuts QOR, right? Now, So that is the prerequisite. It has to cut this in two. That's basically all that is saying. Now, angle OQP is the same as ORP, and that is equal to 90 degrees. And we already have these 90-degree angle here based on what we had from our sixth. We had put them in earlier because we know that at the where the radius is at the point of contact, it's a perpendicular line. And so we had already put that there. So we have this bisector here. And so ORP, which is this angle here, where the radius meets the point of contact of the tangent, is 90 degrees. And it's the same for OQP, where the radius, where this radius here, in this case, it's this radius, meets the point of contact. It is 90 degrees. And QOR, which is QOR, which is this angle here, and QPR, they're equal to 180 degrees. So if you have, just get rid of that, right. So QOR, so this angle here, and QPR, this angle here, are equal. So whatever one is, if one is 80, the other one is 80 as well. If one is 100, the other one is 100 as well, right? Any questions? So this angle and this angle are equal. Any questions? No questions? All right, so if there aren't any questions, we are going to start working through some questions. So I'm going to work through one with you and then give you one to work, and then we're going to go back and forth, right? So give you one to work and then we'll come back together and work it, give you another one, so on and so forth. So let's start. Let's start with an easy one that we're going to work through together. So that's the center of our circle there. I'm going to call our center O. And then that's a line that runs through the center of our circle and touches 2 points on the circumference. So that is, so this line is a diameter. That's L and P, that's the name of it. And then, oops. Wait. All right, that's a little better. Oh boy. Okay. Yeah. Say again. Nope. We'll turn this. Okay. All right. So I'm just going to go ahead and label these things. That's L. That's P. That's O. So the point on the line, that's Q. N M. All right. Everybody ready now? We're going to just go through this. So we're asked to find three angles. We're asked to find L, M, P. We're also asked to find L, N, P. And then we're asked to find Q, L, P. And then L, Q, O. All right, anybody, just by looking at it, let's start with LMP. Do you have any ideas on how we would go about doing LMP? Doesn't have to be right. Just looking for a try. Hold on, I'm missing something. Let me just put in an angle here. I have an angle here of 120 degrees. All right. Amoy or Giovanni, any ideas as to how we would go about solving LMP? So let me highlight LMP for you. This is something that I like to do just because it helps me to just lift one at a time out of the whole mass of thing that's happening here. So this is L on this side here. So I'm looking for L, M, P. So this is the angle that we're trying to find. This angle right here. That's the angle that we're concerned about. Any ideas? Which of the rules we could use to find LMP? Bear in mind, this is the center O, and LP is our diameter. You want to flip through and just tell me any ideas about which of the what do you call it? Which of the theorems, which of the rules you would use? No ideas? They are talking to me. All right. So the important thing here for us to appreciate is that and again, you're going to have to just flip through and look to see what rules apply, right, in the beginning. So I'm focusing in on the fact here that this here, LP, is the diameter. And there is a rule concerning when you have an angle that is at the circumference and it is bound by the diameter, right? Let me see if we can just go back up and find that rule. So here we have it. Remember, we have a rule, two criteria. It is bound by the diameter and it touches the circumference. Whenever that happens, we say the angle that forms at the circumference is a right angle. It's 90 degrees. So for LMP, that satisfies the criteria. It touches the circumference and it is bound by the diameter. So we know that it is a 90-degree angle. So we can find LMP to be 90 degrees because it is subtended at the circumference and bound by the diameter. Any questions on that one? Amoy and Giovanni? No questions. All right. So I'm just going to take off the highlights that I had done for that one. So that we can focus on the next question. So I'm just going to remove the highlights. I'm going to keep the one for the diameter, which is LP. Our next one is LNP. So let's highlight LNP. So L is here. and then N is here, and P is right there. Now, there are two of the rules that we could use that can apply to this. The first one is the same rule that we used above. This angle, it's subtended at the circumference, it touches the circumference, and it is bound by the diameter LP. So we know it is 90 degrees, right? Because that's what the rule says. I can go back to the rule, to that rule for you. It's the same rule we used before, where an angle bound by the diameter touches the circumference, the angle it forms is 90 degrees. But there is also another rule that said if you have an angle and it is bound by the same arc, then the two angles are equal. And we could also apply that in this case here, because it is bound by the same arc. I could draw that arc here. It is bound by the same arc. See there, coloring it in yellow. Both of them are bound by the same arc. So that means that both of them, both LMP and LNP, would be the exact same size, right? Now, the easier way to do it, of course, is just to say that they're both bound by the diameter and subtended at the circumference. The reason I'm going through this one by showing you that they're both subtended by the same arc is that people learn differently and people, identify and pick up on things differently. So whereas it may catch my eye first that they are both bound by the diameter and touches the circumference, you might pick up that they are subtended by the same arc, and so they're the same size. Just pointing out that there are different ways to skin a cat. Both ways in this instance are correct. Any questions so far? We found LNP and LMP. Any questions? All right, so let me just clean this up and then we can move on to our next one. All right, so we're looking to find QLP. So I'm just going to highlight QLP so that we can see it. Q is here. Q, L, am I doing the right thing? QLP, all right? All right, so here we're being asked to find QLP and QOP. Again, you're going to have to do the legwork of just going through all 9 of these. Of course, that's until you are much more familiar, right? But now that we're practicing, do the legwork, go through all 9 of them and see what can work. So for example, if we go through them, we know that this definitely doesn't have anything to do with our diagram there. Don't have anything like that either. We don't have a tangent, so that can't use. Don't have a tangent, so that rule can't be used. We don't have any exterior angles, so that rule can't be used. We don't have any quadrilateral, that rule can't be used. We can go back and check, right? This is just the work that you have to do. So we can check to see if it's bound by the diameter and touches the circumference. So let's go back. Is our angle bound by the diameter and touches the circumference? No, that's not the case here, all right? So we know that that rule can't be used, all right? We can go to the next rule. This rule speaks about 2 angles that are bound by the same arc. So let's see if that can apply. So here we have LMP. So the arc so first of all, if we're going to try and do it this way, this rule has to do with angles bound by the same arc. So let's first identify the arc. The arc in this case would be from this to right here, all right? So we would have to ask ourselves to see if that rule can apply. We'd have to ask ourselves, are there any other angles that are bound by this same arc? Giovanni or Amoy? Come. Are there any angles that are bound by this same arc? No response? All right, so I'm going to show you angle Q, O, P that's bound by the exact same arc as angle QLP. So this is important because it satisfies one of our theorems. Angles bound by the same arc are equal. And we have the size of QOP. It's subtended by the same arc. So that means that angle QLP is also 120, following the theorem that we have here. This one that says angles bound by the same arc measure the same. So that's the one that we would use in this case here. So QLP would equal to 120 degrees. Hold on. I don't think, well, I think there's something else on this one. Let me just, yeah. So this is wrong. So they're subtended by the same arc, but there's also something else going on. I'm going to use this one. This is the correct one to use. Our very first one. So QLP, if you notice, this one speaks about two angles subtended by the same arc, but one of them passes through the center. In our case here, we have we have QOP passing through the center, subtended by the same arc as QLP. So since it's passing through the center, then the rule number 1 would apply, right? Because it passes through the center. So QOP would be 2 times QLP, which means that QLP would be half of 120, which would be 60 degrees, right? Using the first rule, because this passes through the center, all right? Any questions for that one? We just did QLP, and we use the first rule to that one. Any question? All right, so we would have gotten 60 degrees for that angle right there. So the next one that we're being asked to find is angle LQO, all right? Angle LQO. So let me angle LQO, let me highlight it. So this is L here, Q, and O. So we are looking toward finding this angle right here. Now, to find this angle right here, it's pretty easy. We're using angles in a triangle. There are 3 angles. Angles in a triangle are equal to 180. This angle here is 120. Angles on a straight line is 180. So this angle would also be 60, which means that angle LQO will be 180 minus 120. That 120 is 60. 60 here. 60 here. Sorry. 60 here plus this 60 here, 120. And then we would get 60 degrees. So Angle LQO is 60 degrees. Any questions so far? All right, no questions.